So, hello everyone. We will talk about the problems related to week 8 today. So, coming to the first question. So, in week 8, it has been taught about the Fox state. So, we will do some problems about Fox state. So, the question is considering quantum harmonic oscillator with creation and annihilation operators denoted by H dagger and H. So these are the creation and annihilation operators for this quantum harmonic oscillator system. So they are acting on Fock state n, where this n goes from 0, 1, 2, 3 and so on. So what does this n 0, 1, 2, 3 means? This means if this is 1, that means there is 1 excitation in the field, Fock field. That means one particle is manifested in the field. So there are, you can say like this, there is one particle present in this field. Okay, so with an excitation or quantum. So what is the commutation relation between A and A dagger, and what will be the action of A and A dagger on A n? So we are not going to derive anything. I am just going to state what is the relation between A and A dagger. So you might be knowing from quantum mechanics the relation between A and A dagger is like this. The commutation relation is of A and A dagger is 1. So similar to quantum mechanics, this is also same. And the commutation between A with itself is 0. Similarly, the commutation of A dagger with itself is also 0. Right. Then, what will be the action of A and A dagger on this Fock state n? So, as you might be knowing, A is the annihilation operator and A dagger is the creation operator. So what does this annihilation operator does? This annihilation operator means hello. So I just started. Can you mute yourself? Okay, let me tell you the question once again. So in last class, it has been taught about the Fock states, right? So we were doing a question about this Fock state. So the question is, consider the quantum harmonic oscillator with creation and annihilation operators. It's denoted by A dagger and A respectively. So this is the creation operator and this is the annihilation operator, and they are acting on this Fock state. So this state means there are n excitations or n number of particles in that field or in that space, Fock space. Okay, so what is the commutation relation between A and A dagger? So we are not going to derive. I am just simply stating the commutation relation between A and A dagger is like this. The commutation between A and A dagger is 1, and the commutation between A with itself is 0, and A dagger with itself is also 0. So in the next question, it is being asked what will be the action of A and A dagger on this Fock state NK, right? So as this operator's name suggests, annihilation operator, so it will annihilate one particle. So if I operate this on A, so it will annihilate one particle. So the final state should be proportional to n minus 1. So one particle is annihilated, so it is vanished. So the number of, what will be the number of particles? N minus 1. And similarly, A dagger is the creation operator. What does that mean? When this A dagger operate on this state, it will create a particle, so it will be proportional to n plus 1. So one particle is created due to this action of A dagger on this state n, right? So let me write down the proper formula. When this annihilation operator operates on a state, its eigenvalue will be root over of n, and the number, it will depend on this number of quanta as root over, and it will reduce one particle, right? Similarly, when the creation operator, it operates on state, it creates the particle, so n will be n plus 1. And what is the eigenvalue? It will also depend on this number of particles or number of quanta initially, so its eigenvalue will be n plus 1, right? So this was the question, and this is the answer. The commutation relation are like this, and when they are operating on a state, they will give new states with different eigenvalues, right? This annihilation operator will annihilate one particle, and this creation operator will create a particle, and their eigenvalues are like this, right? Okay, then coming to the next question. One second. So the next question says, consider a system of two quanta harmonic oscillators with each with its own set of creation and annihilation operators. So there are two systems of harmonic oscillators, and their creation and annihilation operators are A1. This is the annihilation operator for this system 1, and this is for system 2. And the creation operator for system 1 is A1 dagger. Similarly, the annihilation operator is A2, and the creation operator is A2 dagger for system 2. Okay, so they are going to operate act on a Fock state N1, N2. So we are defining our Fock state in this combination of these two systems, this system 1 and system 2. We are considering them together, so the Fock state describes both the systems together, so it is represented by N1 and N2. So this means there are N1 number of quanta or particles or excitation, whatever you want to say, in the system 1, and N2 number of particles in system 2 initially. So these are the quantum numbers for N1 and N2, so they go from 0 to infinity. Okay, this is the same what I told you right now. So what will be the commutation relation between A1 dagger, A2 dagger. So as in the previous question, I stated the relation between creation and annihilation operators, like the commutation relation between A and A dagger will be 1, right? Now here there are two different systems and they are independent. Actually, they won't impact one another. So the commutation relation for first system between the creation and annihilation operator will be 1. Similarly, the commutation relation between with itself, this annihilation operator with itself will be 0, and the commutation relation of creation operator in this first system also will be 0, right? So similar case will be for the second one also, second system. This will be A2 commutation with A2 dagger. This will be 1, and A2 commutation and A2 dagger commutation. This will be 0, right? Then we have one more choice, like we can take first particle from the first system and the second particle second operator from the second system, like A2. So what will be the situation in this case? Like I am taking the annihilation operator from the first state and the creation operator from the second, it's not state, second system. So as I told you earlier, these systems are independent of each other. So the commutation relation will be 0. Whatever I take, A1, A2 also, this will also 0. Similarly, A2, A1, it's 0 means that same case. A2, A1 dagger, A2 dagger, this will also be 0, as they are independent systems and we are representing them in a single Fock state like this. Then these are the commutation relation for this system, right? So briefly, A1 the commutation of A1 with A1 dagger is 1, A2 with A2 dagger is 1, and rest all are 0, right? Then the next question is find the expressions for the action of these operators on this Fock state N1 and N2. So we have this state N1 and 2 Fock state, right? So we want to find the action of these operators A1, A2, A1 dagger, A2 dagger on this Fock state. So as I told you earlier, the annihilation operator will annihilate a particle and a creation operator will create a particle. But these are for two different systems. So A1 is for first system and A2 is for the second system. So they will annihilate particle in their system. So if I apply A1 on this N1, N2 state, what it will do? It will annihilate a particle in its system. So this first number is represents the number of excitation or particles in the first system, right? So it will annihilate a particle in its system, but it can't affect the second system. So the second system will remain as it is, right? So you know the eigenvalue also, it will depend on the number of particles in that system. So it will be root over of n1 minus 1, and right, this is when this annihilation operator operates on this Fock. Similarly, if A2 will operate on this Fock state, this will be N2, N1 will be unharmed, and N2 will change by one particle. Right. Now let's see the action of creation operator on this Fock state. So as you might be knowing, creation operator creates a excitation or creates a particle in its system. So this subscript represents the first system. So it will create a particle in the first system. So it will be proportional to n1 plus 1, and the second system will be unharmed. So it will remain as it is. Right. So what will be the eigenvalue? So the eigenvalue is dependent on only the first system's particle number. So it will be n1 plus 1. So this proportionality will go, and this is equal. Right. So similarly, if I operate A2 dagger on this state, then it will become n2 plus 1, n1 comma n2 plus 1. Right. So this is the answer for that. So each creation of an annihilation operator, they will act on their own system. They can't affect the number of particles in the different system. Right. Like if you consider the n1 is for fermionic field, and n2 is for some bosonic field. I am telling him vaguely, like for example. So if a annihilation operator of fermion will operate on this state 1 and 2, so this annihilation operator can annihilate one fermion. So it will ultimately impact the number of fermions. It can't change the number of bosons in the system. Right. So this is just to make you understand. So similarly, if you operate a bosonic creation operator, then it can't change the fermion number. It will change the boson number. Right. So they are independent of each other. Right. Okay. Any questions? Okay, then we'll move on to the next question. Okay. So the next question says, consider a quantum system with two states, 0 and 1. That means there is 0 particle and 1 particle in this state. And a set of creation and annihilation operator A dagger and A, satisfying the commutation relation like this. Then define a state psi, which is a linear combination of this 0 and 1, and this phi is a real parameter. It's just a phase of acting on this state 1. Okay. Then calculate this A dagger A on this state psi. Right. and simplify the result as much as possible. Okay, so we know when a annihilation operator operate on state n, what is the eigenvalue? This is root over of n, and what will be the state? This will be n minus 1, right? Similarly, okay, so this is annihilation operator. Then when a creation operator operates on a system n, then its eigenvalue will be n plus 1, and the eigenstate, the number of particles will increase by 1, right? Now okay, this is that. Now we see when I apply a dagger on a or a n, what, let's write it n first. Or you can let me write this way. This is a dagger a acting on n. So this operator is in vicinity with n, so it will act on n first, right? So this is an annihilation operator. So what it will do, it will annihilate a particle and its eigenvalue will be root over of n, and its state will be n minus 1, right? Now it's a eigenvalue, so the operator can't impact this eigenvalue, so it will go outside. Okay, then a dagger will act on n minus 1, right? Now you know when a dagger acts on a state, this eigenvalue becomes n plus 1. So when it acts on n, so this a dagger acting on n minus 1 will be root over of n minus 1 plus 1, right? This is you can assume n, then this is plus 1. Then what will be the impact on eigenvector? It will be increased by 1, so n minus 1 plus 1, so it will be n again. So this is n minus 1 plus 1, this only root over of n. So ultimately this is n. So you see this operator a dagger a, when acting on n, is giving the number of particles in that state, and it's just a dagger a when acting on n, this is simply spitting out the number of particles in that state. And you see this state is also not changing. Then what is this system is called? This is a eigen system. When the state is remain constant, then this system is called eigen system. An operator is acting on this state, and it's giving some eigenvalue, and the state remains changed. So this kind of system is called eigen system. So this is the eigenvalue then. So you see this operator acting on this state is spitting out the number of particles in that state, right? So we can name this operator as number operator. So it's spitting out the number of particles in the system. So this is number operator. So we have a state like psi is 1 over root over 0 plus e to the power I phi is 1. So in this system there are only two states, 0 and 1, right? So when this number operator acts on this state psi, or this dagger A operates on this state psi, what will happen? We can directly apply this. So this is a linear system, so this operator act on this state linearly, so it will impact each of the term individually. So for the first term it will be 1 over root over 2 this a dagger A acting on 0, then plus 1 over root 2 e to the I phi, it's a number so I can take it out. This will be a dagger A acting on 1. So we saw that this a dagger A acts like a number operator, so its eigenvalue will spit out the number of particles in the system. So for the first case there are 0 particles in the system, so it will give eigenvalue 0. So first term will be 0. 0 into 0 eigenspace, so it's a 0. Then the second term, this will this number operator acting on this state 1, it will give eigenvalue 1. So this will become the I phi state 1. So this answer will be 1 over root 2 e to the I phi 1 when this operator a dagger A operator operates on this state psi, right? So any questions so far? Okay. Then we'll move to the next question. Okay. So this question says, consider a quantum harmonic oscillator with anharmonic potential. So this potential term, and this is harmonic potential, but it's with this one extra term is there, lambda x to the power 4. So this makes this potential as anharmonic. So in a harmonic system, you know the Hamiltonian is p square over 2m plus half m omega square x square. So now, so this is the kinetic term and this is the potential term. Now one extra term is added, lambda x to the power 4. So this term makes this system anharmonic. Okay. Now m is the mass of the oscillator, omega is the angular frequency, and lambda is the anharmonic coupling constant. Okay. So and x is the position operator. Okay. Then calculate the energy eigenvalues and eigenfunctions for this anharmonic oscillator to first order perturbation lambda. Okay. So we know the energy for this part. This is simply the harmonic Hamiltonian, harmonic oscillator Hamiltonian. So we know the energy for this state. This will be n plus half h cross omega. Okay. So where this omega is the frequency and this n is the quantum number which goes from 0, 1, 2 up to infinity. Okay. Now we have an extra potential lambda x to the power 4. So we are being asked calculate the eigenvalues. That means eigenvalue of Hamiltonian means NH, and the eigenfunction of this uh, anharmonic oscillator. Okay, so if we have a state like n, then for this state the energy is n plus half h cross omega. Okay, this is for harmonic case. So for anharmonic case, what will happen? So uh, this means what? When Hamiltonian operates on this state n, it spits out as En, or as En plus half h cross omega n. Right. Now this is up to the term half m omega square x square. Now we have an extra term, so it will be added as a perturbation. So we can take care of it as independently as lambda x to the power 4 acting on this state n. Okay, so if we want to find the energy, then what we will do? We will operate a bra on the left hand side. You can see here we have h operating on n is giving E as eigenvalue and state n. So if I want E, then what I will do is h and is E. Okay, so if I want E, then what I will do? I will operate a n state on this equation, then this will become n h n. Okay, so this is the number, so it will go out E n, and this is n h n. So the Fock states are orthonormal, so n bra n ket n, this will give 1. So E is simply n h n. Okay, so if we want a correction term, let's say E1 to this harmonic system, then this will be the form of this energy in bra lambda x to the power 4 n E1. Okay, now this x is the position operator. Okay, so we have few questions back we were dealing with creation and annihilation operators, right? And I have a state here as n, so it will be easier for me if I convert this position operator into creation and annihilation operator. So the position x can be written as 1 over root over 2 m omega a cap plus a dash. So this is the position operator in terms of creation and annihilation operator. Okay, now I'll operate this lambda x to the power 4 on, let me put this value here, then lambda is a constant, I can take it out, and this 2m omega is also constant, so it will also go out. So lambda it will become 4m square omega square. Okay, now I have n a cap plus a dagger to the power 4 n. Right, now I need to solve this. Okay, so I can do one thing, I can write this as a cap plus a dagger whole square to the power 2. Okay, now I have to just calculate this first. So a cap plus a dagger cap square is nothing but a cap plus a dagger into a cap plus a dagger, right? So this will give a square plus a dagger square plus a dagger plus a dagger a. So we know that this operator represents the number operator, right? But we don't know this operator a dagger, so we need to convert it to number operator. How we will do that? Actually, we have this commutative relation between a and a dagger, right? This is simply 1. So from this relation we can find this one. So this will give a dagger minus a dagger a as 1. So from this relation we can find this a dagger is 1 plus a dagger a. So these are operators, so you have to give them a k. Okay, and this one is also an operator. When it operates on a state, it keeps the state as it is. It doesn't change the state. Okay, so this term will become 1 plus a dagger a, right? So now this square term this will become a square plus a dagger square plus 1 plus 2 into a dagger a, right? Now this I took a plus a dagger square. I have a plus a dagger to the power 4, so I have to take the square again. Okay, now if I do the square, so then I will get some terms like a to the power 4, a dagger to the power 4. So when this a square or a to the power 4, it will operate on a state eta n. So what it will do, it will spit out some eigenvalue and it will change the state to, like, if a square is operator, it will give n minus 2. This annihilation operator is operated twice, so 2 particles will be annihilated. Or if I operate a to the power 4, then 4 particles will be annihilated from the system. Okay, so but in the bra we have n number of particles. Okay, and in the cat we have n minus 2 or n minus 4, something like that. And if the creation operator will operate also, then it will a dagger square will give n plus 2, or a dagger to the 4 will give n plus 4, something like that. So ultimately I will have different cat state in the right hand side. So as these states are orthonormal, then this will give to 0. So simply I can ignore these terms, right? Then I have to effectively calculate 1 plus a dagger no, I can ignore from now, because from this also I'll get some cross terms. So let it write this way. So I have a square. I'll ignore them after making this square. Okay, I'll take them as 0. So a dagger square plus 1 plus 2 a dagger a whole square. So I have to find this. So this will become um, let's take these two terms as one. So this is a plus b plus c something. So this will become a square plus a dagger square whole square plus 1 square plus this 2a dagger a square plus then 2ab means 2 into this a square plus a dagger square plus 2bc is 2 into 2 a dagger a plus 2ca 2 into a dagger a into a square plus a dagger square. Okay, now you can see we just want to find when we just want to extract the useful things from this term, then we will neglect all other terms. So you see from this term there is a square and a dagger square, so it will ultimately change the case state. So I can securely take this to be 0. Okay, so similarly if I multiply a dagger a with a square, then it will give a dagger a cube or a dagger cube a. Ultimately these terms also will modify the case state, so this term also I can take to be 0. So I am left with these and I have to solve this first. Okay, then this will be a to the power 4 plus a dagger to the power 4 plus this will be a square a dagger square plus a dagger square a square. Then the rest terms I can write as 1 plus 3, this is 2 into a dagger square a square, then plus 4 a dagger a, right. Then these are the final terms. So I can neglect this because these will change the case state, right. So the terms like a dagger I have to consider. Now you see a dagger, the number operator is a dagger a, right. So it will give me the number of particles in the state. So I have this kind of terms here, right. Then I have to change this using the commutation relation a dagger equal to 1. So from this I will get a dagger as 1 plus a dagger a, right. So I have to put this in this formula. So let me collect all the terms first. So I have 3 a dagger square a square, then 1 plus 4 a dagger a, then this term I can write it as 1 plus a dagger a whole square, right. So now it's almost done. I just have to find this term. So this is 3 a dagger square a square plus 1 plus 4 a dagger a, then this will be 1 plus a dagger square a square plus again, so this is a dagger a into 2. Okay. So now it's done. Okay. So ultimately I have 4 a dagger square, this is 1, this is 3, 4 a dagger square a square plus 1 plus 1 is 2 then I have 6 a dagger a. Right. I don't know where did I make some mistakes. You can verify by doing yourself. So for now I got this as the final operator. Okay, so I started with a plus a dagger to the power 4 operating on the state eta. So it is finally giving me 4 a dagger square a square plus 2 plus 6 a dagger a theta. Sorry, not theta, it's n. So I don't know if I did some mistakes during the calculation. You just can check this and verify. So the idea is like this. Okay, so you know this is n is the number operator is a dagger a, right? So I can simply take it as n square plus 2 plus 6 n. This is 4. Okay, so this will operate on state n, right? So this will give me as 4 n square plus 2 plus 6n. This is the eigenvalue, right? So I need to find this bra n, this term k. So I have to apply bra n here. So this is simply a number. So these states are orthonormal. So n, bra and ket n, they will give 1. So the final answer will be 4 n square plus 6n plus 2. Right. And we had some constants. Initially lambda divided by 4n square omega square. So this will be lambda divided by 4n square omega square. So this is the energy correction to the first order due to this additional term lambda x to the power 4 to the Hamiltonian. So the energy correction to the system due to this anharmonic term is this. So this will be simply added to the harmonic oscillator energy n plus half h cross omega, right? Okay, so any questions so far? Okay, then we'll move to the next question. So the next question says an electron of mass m and charge -e moves in a region where uniform magnetic field B exists in z direction. So there are magnetic field in z direction, that is Bz, and one electron is moving in this uniform magnetic field. Okay, now set up the Schrodinger equation in rectangular coordinate, or that Cartesian coordinate. So let me write down the Schrodinger equation first. So this Schrodinger equation is h psi, or you can write it as k psi. H psi is E psi, right? And this H form is E square over 2n plus potential E of r psi is E psi, right? So this P is the total momentum of the particle and V is the potential. So if a charged particle uh, is inside a magnetic field, then its momentum actually changes. So how it changes? So this P goes to P plus E over C A, where this A is the vector potential. You can see this A coming in the magnetic field, right? So this is the vector. So this P is momentum. If the charge particle is inside a magnetic field, then its momentum is modified like this. So the momentum will be modified like this, and we are not told about any potential, so we will take V of R as 0, right? So finally what I have, my Schrodinger equation initially it is H is equal to P square, so P will be modified, P square over 2m, so this will become P plus E over C A divided by 2m, this also. Okay, so we are given an electron with charge minus E, so this plus will become minus. So this is my Hamiltonian, right? So I have to write this in terms of magnetic field which is applied in the z direction, right? So my magnetic field formula is like this. This is gradient of, no, this is curl of this vector field. Okay. So B is applied in the z direction, right? So let me write down each component. So Bx is del one second. So Bx can be written as Az divided by del y minus del Ay over del z, right? So similarly By is del Ax over del z minus del Az divided by del x, and Bz is del Ay over del x minus del Ax divided by del y, right? Now the magnetic field is applied on z direction, right? So only this term should survive. This should give B, and these two should give me 0. So accordingly I have to choose A, this vector, right? So now if I choose A vector to be like Bx yk, now you see this this will satisfy all this equation. Now this is yk, that means this is Ay, right? And all other components are 0. Ax is 0, Az is 0. So if you put this in the above equation, you will get this term Bz equal to B for this choice of A. A is Bx yk, right? Now I have the form of A. Now I can substitute in the above equation, right? So if I substitute A in the above equation, so you see this is only in y direction. So I can write AY equal to B, right? So I have Hamiltonian, like we have already got the solution. We are just simplifying this. Okay, so as we are being asked to simplify, so this is uh, okay, this is momentum P. So this momentum P will contain Px xk plus Py yk plus Pz zk, right? Now I have a term like P minus E over C A vector, right? So each component of A will be added to each component of P, right? So the x component of A will be added to the x component of P, and similarly all the four other. So you see there is no x term for A. So the x component will remain as Px, right? And there is no x component, so it will be Px square divided by 2m. But I have a y component of A. So the second term which will be come with Py will be Py minus E over C. Now Ay is Bx. So this is Bx over 2m, and this is square. And there is no z term for A also, so my Pz will also be written like. So let me write down the total Hamiltonian. S is Px square divided by 2m plus Py minus E over C Bx whole square over 2m plus Pz square over 2m. So this is my total Hamiltonian in the magnetic field B, which is applied in z direction, right? Now we are being asked to set the Schrodinger equation for this kind of system. So what is the Schrodinger equation? So Schrodinger equation is H psi equal to E psi, right? So I have to just operate psi on both of the sides. So this will give energy E psi, right? Now, so the first question is done. This is the Schrodinger equation for a electron in the magnetic field which is applied in z direction. Now, coming to the next question, solve the equation for all the energy levels. Okay, so we need to find the eigenvalue. Okay, now I need to find E, right? Now from the second term, let me take common this EB divided by C. Let me take common. So the second term will become EB over C is taken common, so it will become C Py divided by EB minus x square, right? Now okay, Okay. So I made a mistake here. So in a magnetic field, the momentum change as P minus E over C by A. As electron charge is minus, so it will become plus. So in every term, so it will become plus. Right. So this is plus. Now let me take this x plus cpy over eb as some other variable. Let's take it to be zeta as x plus cpy over eb. Right. As it is dependent on x, let me take one more as p zeta as px. Right. Then my Hamiltonian will become, or let's write the Schrodinger equation itself. So px was there in the first term, so this will become p zeta square over 2m. Then in the second term I wrote like this. So this is zeta now plus 1 over 2m and eb over c. Then this is zeta square. Right. This is the second term. Right. And in the third term I can take to the right hand side as e minus pz square over 2m, and these are acting on the state psi. Right. Now you see, if I take this constant as something like omega square, then this will become p zeta square over 2m plus 1 half. Okay. Half m omega square should come, right? So let me multiply. Okay. So it came out of a square, right? So it's a square. E b over c, right? Now it's a square. So I need a term like harmonic oscillator. So I need a term like half m omega square x square, right? So I need to somehow get a m here. So for that, let me multiply m square here and m here. So m square will cancel. So it's same. So this term I am taking as omega square. So finally I have half m omega square zeta square, and this is operating on the space I, and it's giving, let's write this energy as E0. So you see, my system is now effectively a harmonic oscillator system, right? So for this system I know the energy, so E0 will be n plus half h cross omega. This is the energy we know for harmonic system. So omega we have in this form, and E0 I have rewritten as this E minus pz square over 2m I have rewritten as E0. So I can substitute back its value. So this is E minus pz square over 2m plus, okay, so equal to n plus half h cross omega's value I have as omega square value is E b over c n square. Right. Now I want the energy, so I will take this part to the right hand side. So this will become pz square over 2m plus n plus half h cross e b over mc square. So this is the eigenvalue for my system which is in a magnetic field applied in z direction, right? So this is the answer. Now coming to the next question. So next question is discuss the motion of electron. So I got a system like my Hamiltonian is now like this. So this part it represents the harmonic oscillator part. This is harmonic oscillation, and this is simply a momentum in z direction, right? So this term is saying me that the particle is moving in z direction with momentum pz, and this part is showing me that this is behaving as a harmonic oscillator. So how does the harmonic oscillator behave? So I am stuck with other two variables x and y. So it is moving in z direction. So this term explain the rotation in xy plane, right? So if I take x in this direction and y in this direction, so the particle is moving in z direction and it is rotating in xy plane. So the particle's motion is now helical. So due to this applied magnetic field in z direction, this electron is moving in z direction, but it's circulating this field also, right? So the motion is helical. Now, so this is the answer. The motion is helical in this magnetic field. Okay, so any questions so far? Okay, so no response means I assume no question. Okay, we will go to the next question. Okay, so the next question says write down the Hamiltonian for a spinless charged particle in a magnetic field and show that the gauge transformation where this vector potential is transformed like this: A plus gradient of some scalar field. Fr is a scalar field. Right, is equivalent to multiplying the wave function by a factor e to the power I EFR by h cross c. So it's saying that we have to show that due to this gauge transformation, A prime, this A going to A prime, which is equal to A plus gradient of f. Due to this gauge transformation, our state or wave function, this will just transform to, just let not write it as state, psi prime, which will be e to the power I E f by h cross c times psi of r. So we have to solve this. Then what is the significance of this result? Then consider the case of uniform magnetic field in this in the z direction. Then show that the energy level will be written as this, and discuss the qualitative feature of the wave function, and we are given the hints like this: a is in x direction and its magnitude is minus bu. Okay, so let's assume this a is transformed into a prime of, sorry, this is not e, this is r. So a of r is a prime of r, which is equal to ar is transformed into a prime r by this gauge transformation, which is equal to a of r plus gradient of this scalar field f of r, right? And let's assume this our wave function psi of r is also transforming like psi prime of r, which is equal to e to the power I e f of r by x cross c psi of r. So let's write down the Hamiltonian first. Okay, in presence of magnetic field, the momentum changes to P minus E divided by C into A, right? This is momentum in the magnetic field changes to like this. Okay, so we are given a charged particle, and it's not mentioned that it's an electron, so we will keep E charges plus E. Okay, so its sign won't change. So now I can write the Hamiltonian as P square over 2m, or it will be P minus E over C A square over 2, right? Right. Now it is given A is in x direction, so A is minus b y x cap, right? Now I can write this Hamiltonian explicitly as px square divided, okay, px, this is the x component, so px will be changed, so px minus e over c, and minus by is there, so it will be plus by square divided by 2m. Then other terms will not change because there is no component of a in that direction, so other terms will remain as it is. So py square divided by 2m, then pz square over 2, right? Okay, now I have the Hamiltonian. I can write down the Schrodinger equation for this. As its psi of r is E psi of r, right? Now I have transformed a to a prime and psi to psi prime. So in this transformed wave function and transformed vector potential, what will be the Hamiltonian? Oh, sorry, Schrodinger equation. So it will become h prime psi of r equal to e okay, let's just operate. Okay, so e psi of r, psi prime of r, right? Energy may change. Okay, h prime I have, let's take this form, h prime as p minus e over c a prime, as this a is transformed into a prime, so this square divided by 2m, right? And my psi prime r is nothing but e to the power I e f of r over h cross c into psi r. So let's check what is h prime psi prime of r. So this will become, or we have to calculate for square first. So let's check for the fact is p minus e over c a prime. When it operates on psi prime r, how it behaves, then we will square it, or we will operate one more p minus e over c a prime, then this will become p cap psi prime of r minus e over c a prime r operating on psi prime of r, right? Now my psi prime's form I know, I'll just put it, p cap psi prime is e to the power I e f of r over h cross c psi of r. Alright, now minus I have this e over c. Now a prime is a plus a prime is a plus grade of f of r, right? Gradient of f of r, and this psi prime is e to the power I e f divided by h cross c into psi of r, right? Now this p operator, you might be knowing, p operator can be written as h cross over I gradient. So if I write this as, let's evaluate this term, so this will be h cross over I gradient of this whole e to the I e f of r h cross c psi of r. I am taking on the first term only, right? Now this gradient, this is nothing but del square, no sorry, del over del r, right? So it's a derivative with respect to r, so I have to apply chain rule, because this exponential function is also dependent on r. So it will be h cross over I. When I operate this del on this, it will become e to the power I e f divided by h cross c gradient of f of r times psi of r plus h cross divided by I, this I e f of r by h cross c gradient of psi, right? So from the first term I got these two terms, right? Now you see in the second term of this if I expand this second term, I will get a term like gradient of f of r e to the power I e f by h cross c divided psi of r. So okay, I took the derivative with respect to this e to the power this function, right? So chain rule will apply, so I will get I e over h cross c, right? So I will cancel, h cross will cancel, so I will be left with e over c. So e over c, this e to power this term gradient of f of r psi of r. So you see this is plus, and from this term I will get a minus. So these two terms will cancel, so I will be left with this term h cross over I e to power this term gradient of psi of r minus e a over c psi of okay. From this I will get this okay, this bracket is here, so I will have e to the power this term psi of r, right? So effectively you see one second. Okay, so you see this e to the power is common in both the terms. I can take this e to the power I e f over h cross c to outside, then I will be left with h cross grade divided by I minus EA over C acting on psi of r. So you will see this is nothing but operator P. So this is e to the power IEF f of r h cross C. This is P minus EA over C psi of r. So we started with this. We operated P minus E over C A prime on psi prime. So we got P minus E A prime over C. We operated on psi prime of r, and we got this. Let's operate again this P minus E A prime divided by C once again from left hand side. Then we will get square psi prime r as, if I operate it once more, I will get the same e to the power I E F by h cross C, and this value, this will be squared A over C square psi of r. So you see Now I can divide 1 over 2m on both the sides, and I can take 1 over 2m here. So this is h prime acting on psi prime of r is giving me this is nothing but h. So this is giving me e to the power I e f by h cross c h psi of r. So you see, when I transform this vector potential to a prime through this gauge delta of f, and then my wave function is just shifted by this term e to the power I e f by h cross over c, right? You see, in this Hamiltonian there is dependency on the vector potential, right? When this particle is inside a magnetic field, then the momentum changes to E minus E over c a. Now we are gauging this vector potential as a plus grade of f, right? Due to this gauging, what is happening? You see, our wave function is just simply multiplied with this phase factor e to the power I e f of r divided by h cross c. So due to this gauging, the wave remains and the equation remains invariant. It's just shifted by this phase e to the power I e f of r divided by h cross c. So our Schrodinger equation is gauge invariance. Okay. So this was the first part. So now it's saying that consider a case of uniform magnetic field in the z direction, and so that the energy level will be written like this. Okay. So we have written the Hamiltonian explicitly like this, right? In the presence of this vector potential A, which is written as minus B is given, right? Minus B by x cap, minus B by x cap. So in the presence of this vector potential, our Hamiltonian will take the form of this, right? So let's put this in Schrodinger equation. X psi equal to E psi. So we got our Hamiltonian as Px okay, Px plus E over c By whole square E over c By whole square over 2n, then rest are same, Py square divided by 2n plus Pz square divided by 2n, and this Hamiltonian is acting on this wave function psi of r, and it is giving energy E, right? Now let me take common this Eb over c from the first term. Then the first term Px plus Eb over C, this y is there, whole square is there. Let me take this as common, EB over C whole square will be taken common, then it will become CPX divided by EB plus y, right. So why I am taking this common, I'll perform similar procedure as the last question to find out the um, energy, effective energy in the presence of this magnetic field, right. So I need to change this Schrodinger equation into the form of harmonic wave equation, harmonic Schrodinger equation. So let me okay, then let me take this as minus y0, then my Schrodinger equation will become this EB over C whole square is there and 1 over 2m is there. Then I am taking this term as minus y, so effectively I will have y minus y0 whole square plus 1 over 2m py square, and let me take this pz square to the right hand side, and then this is phi of r, this will become E minus pz divided by 2m pz square divided by 2m psi of r, right. Now you see I have the form. Now if I take this as x square and I just multiply m square here, then multiply m square here, then this is half m, this term E B over C m whole square. So I can take this as omega square. So effectively I have here half m omega square x square, right. And from this term I have some sorry, this is dependent on y, so this is p this y minus y0 square, and this is py square divided by 2m. So you see I got a Hamiltonian like simple harmonic oscillator. So if I assume this energy to be E0, so then I know the solution. E0 is nothing but n plus half h cross omega. So my omega is here. My omega square was EB by Cm. So my omega will be EB over Cm, right. And my E0 is E minus Pz divided by 2m n plus half h cross omega is EB over Cm. So finally my energy will be n plus half h cross EB over Cm plus Pz square over 2n. Or you can write this operator in terms of eigenvalue. If Pz will give some eigenvalue like h cross kz, or it's not exactly eigenvalue, it's a different form where this is kz is wave vector. So I can rewrite this term as h cross square kz square divided by 2. So my energy of the system in the presence of this external magnetic field is this, right? Now so I got the eigenvalue. Eigenvalue means I got the energy of the system. This is the eigenvalue of Hamiltonian, right? Now I'm not going to detail, but we can write the wave function from this also. I'm just giving you the exact solution for this. So we can perform something like some space. We had psi of r initially, so psi of r is nothing but psi of x, y and z, right? And we got our Hamiltonian like this, right? So you see in our Hamiltonian we have y dependency here. So my Hamiltonian depends on the variable y, px, py, pz, right? Now if I take commutation of px with respect to Hamiltonian, there is no x dependence here, so it will give me 0. But and similarly for pz case also, pz h, there is no z dependence here, right? So if I take py commutation with h, there is a y dependence here, so we know the commutation relation y py, it will give ih cross commutation. So similarly it won't give me 0 for py case. So we see we can form a complete set using this px, pz and the Hamiltonian if they are commuting with the Hamiltonian, but I can't take this py variable. So I can write my wave equation as e to the power, my wave function will take the form e to the power I pxx plus pzz divided by h cross, and I am writing this y dependency of the wave function as some other form chi of y, right? Now if you put this wave function in this Schrodinger wave equation, then you will see this part is only a phase, so this psi will give me or effectively I can write my wave equation as h operating of chi of y equal to e chi of y, right? So you see the x and z variables, they became a function like phase for this wave function, right? Now I'm simply now not deriving anything. We can write this wave function as it is this psi is dependent on px, pz, and this Hamiltonian is quantified by this quantum number n, then n. So this wave equation can be written as this phase factor e to the power I pxx plus pzz divided by h cross, and from the y part we will get e to the power minus eb divided by 2h cross c y minus y0 square, and hn, which will be a function of eb divided by h cross c y minus y0, where this hn is the Hermite polynomial. This is Hermite. Right, so this is my wave function in the presence of this external magnetic field which is applied in z direction. So I got the eigenvalue, and now I got the eigenfunction also in this form. Right, so any questions so far? Okay, if there is no question, then we will move to the next question. Okay, just give me a second. Okay, let's move to the next question. Okay, determine the energy levels and their degeneracy and the corresponding eigenfunctions of an electron contained in a cube of essentially infinite volume L cube. The electron is in electromagnetic field characterized by the vector potential this, right? Just give me a second. भैया मेरा एक पार्सल आया है, तो आप ले लोगे थोड़ा, इस नंबर को कॉल करके जाओ। मैं अभी क्लास में हूँ, मेरा पार्सल है, बात करके। वो शायद यूनिवर्सिटी के बाहर होगा। हेलो, यहाँ पे नेटवर्क नहीं आता। आप ले जाओ फ़ोन, मैं क्लास में हूँ, अभी ख़त्म हो जाएगा 15-10 मिनट। Okay, so the question says determine the energy levels and their degeneracy and the corresponding eigenfunctions of an electron contained in the cube of essential infinite volume L cube. So we have a potential of infinite volume L cube, where this L tends to infinity, right? Now this electron is in an electric field and this vector potential is in y direction. So my magnetic field is nothing but del cross A, right? So I have a applied magnetic field. Now I need to find the wave equation for this. So I know the wave equation as H psi equal to E psi, where this H I can write as 1/2n px square plus, you see, this vector potential is applied in y direction. So my py will be modified, py minus e over c, which is h0 x, right, this square divided, okay, 2m is outside, and pz square, right. So I have a Hamiltonian like this in this with the given vector potential in the y direction, right. Now I can perform the similar operation, like I can take common this part, EH0 divided by C, then I will take the rest of it as some other variable. So let me take common from this part. I have py minus h0 x e over c whole square. I am taking common e h0 over c whole square, then, or I can take common minus h0 e over c, then effectively I have this square, then it will become x minus c py divided by h0 e whole square. Now I can take this variable as some other variable, some chi, and I can perform the similar operation to find out the eigenvalue or energy, right. Or I can take this as x0, then it will be a shift only in x direction. Then so what will be the omega in this case? Omega will be ES0 by Cn. You perform the same procedure, you will get omega like this, right. And my x0 is C Ey by S0 is, right. Then I can, similar to the last two question, I can take pz to the right hand side, then that I will name as E0, then E0 will be n plus 2 n plus half h cross omega, then this E0 is nothing but E minus half pz square divided by 2m equal to, this is n plus half h cross, and omega I have as E h0 over mc, right. Then my eigenvalue will be equal to n plus half h cross E h0 over mc plus pz square over 2, right. So I got the eigenvalue of h, which is energy. Now I need to find the eigenfunction. So you see, in this equation there is no y or z dependency, there is only x dependency in there. So I can take py h commutation as 0 and pz h commutation as 0, right. So my the py, pz and h will form a complete set of solution. So I can rewrite the wave function psi of xyz, or this will become now a function of p, py, pz, and h, py, pz. This is n, and this will become e to the power I pyy plus pzz divided by h cross, and the rest I can write like this. This chi function will be dependent on x. So you see, this y is decoupled with respect to with this y and z variables. They are, or this py, pz variables are independent of this px, and they are commuting with this Hamilton. So I can write those parts as phase, and I am left with this x variable, right? So my final solution I am just writing in terms of this Hermite polynomial as psi of r. This will become c of n e to the power this part I, this pyy plus pz divided by h cross, and from the x part I'll get something like e0 by 2x plus c x minus x0 whole square times the Hermite polynomial, which will depend on this minus e f0 divided by h plus c x minus x. Right. So we had a system where this magnetic field is external magnetic field is applied. Now in the presence of this external magnetic field, we are getting the eigenvalue or the energy of the system like this, and our wave function is modifying to this. Right. So any questions so far? Okay. Okay then. So there are some questions. Okay. I have one more question. So consider a quantum system described by this Hamiltonian H with eigenstate as psi of n and corresponding energy are En, where this n is a quantum number. Then the system is initially in superposition state as this at time t0. This was the state of superposition of these two states, psi1 and psi2. Determine the energy of the system. What is the possible outcome? So we are being asked the probability at time t. So my system is at time t equal to 0 as psi of 0. This is 1 over root 2 psi of 1 plus psi of 2. Right. Now I am asked at t equal to 0 what is the probability of each case. So for probability of finding the state psi 1 at time t equal to 0 is nothing but this psi 1 operating on psi 0. This is the probability density. So to find the probability I have to take the square. Right. So I am assuming these two are orthonormal. So this psi 1 operating on this state will give me 1 over root 2 whole square, which is half. And similarly p of I2 will also give me half, right? So now moving to the next question. Consider a quantum system described by this a single mode of bosonic field. The creation operator and the annihilation operator are given like this. The Fock space, the system spanned by this state where n goes from 0 to n. In particular, suppose the system is in Fock state 2 at time t equal to 0 and evolves according to the Hamiltonian like this, where omega is a constant. What is the state of the system at time equal to t? So we are given the Fock state n, right? And the Hamiltonian is given like this: h cross omega a dagger a plus r, and we need to evolve these states with respect to time. So initially it was like eta, so we need a unitary operator. What is the form of this unitary operator? I can write this unitary operator form as ut equal to e to the power minus I over h cross h, this is not a function, h cap t, right? So this unitary operator, it will describe, or it will encode the information of evolution of the states with respect to time. So you see this function is dependent on Hamiltonian, so I can rewrite this as I over h cross omega a dagger a plus half into t, right? So h cross cancels. This is u of t simply e to the power minus I omega a dagger a plus half t, right? So to find, so initially the question is like I have to evolve this state 2, right? So it was at time equal to 0, initial state was 2. So as time evolves, the state 2 will evolve, and this evolution will be mediated by this unitary operator operating on this state 2, right? Now you know the effect of this number operator on any state. It will give n, right? Now I have e to the power minus I omega a dagger a plus half of t operating on this state 2. Now as this is a number operator, if I operate this on the state 2, what I will get as the eigenvalue, I will get e to the power minus I omega 2 plus half t 2, right? So this is e to the power minus I omega 3 over 2t 2. So as time evolves, this state evolves to this state. This state 2 evolves to this state, right? So as it is time now, we will stop here. Okay, all the best for your exams. Okay.